Good evening, everyone. Today we'll begin with our module 2, that is uniform flow. So in that first lecture, we'll discuss the basics of uniform flow and resistance equations. So the learning objectives of today's lecture are: understand the establishment of uniform flow, derive the basic resistance equations for uniform flow condition, and analyze the factors affecting surface roughness. So by definition, the uniform flow is one where the flow properties such as depth, velocity, and discharge remain constant with respect to distance. So in case, for example, a prismatic channel which carries a constant discharge at a constant velocity can be considered as a uniform flow condition. So a uniform flow is always a steady flow. So unsteady uniform flow would never exist. Now, there are certain criteria to qualify for the uniform flow. The first criteria, as defined, that is the depth, water area, velocity, and discharge at every section of the channel reach are constant. Now, this essentially implies that when the water is flowing, there are three components to it. If we look at this figure, so here the first component, that is the channel bed, which is this denoted by S naught, the channel bed slope. Second is a water surface, that water surface slope is SW, and third is the energy line, that is depth plus V square by 2G, and that is the total energy line, and the slope is SF. So if all these three slopes are equal, that implies that these flow, that is the energy lines, are water surface and channel bed are parallel, then we can say that the uniform flow condition is established. So these two are the essential criteria to establish the uniform flow. Now, there can be a small discussion that could uniform flow occur where where there is channel with steeper slopes and where the flow velocity is very high. So based on these two criteria, let us analyze whether the uniform flow can occur or not. So moving ahead, that how the uniform flow is established. In nature, it will never be like that the uniform flow is established from the inception of the flow. So what happens that let us say the condition is that there is a lake with the certain water level, and water level slowly gushes out of the lake, and where the uniform flow condition will be established, that is our area of interest. So when the water from the lake slowly enters the channel, the velocity and resistance are very small, and the resistance is outbalanced by the gravity forces, which will result in some accelerating flow in the upstream reaches. Now, as the flow occurs, gradually there will be an increase in the velocity and resistance until a point where these two are balanced by each other. So once the resistance and velocity are balanced at this moment, and after that the uniform flow conditions are established. So till where these two forces are in balance, the uniform flow conditions will prevail. However, they are likely to change if there is some change in the topography, cross section, or any other properties. So moving further, here we can see a more detailed view where the forces are marked. So the resisting and the driving forces, when they balance each other, there the uniform flow condition is established. So in the longitudinal view, we take an elementary section of length delta x. So the driving force, that is Fg, in the direction of flow, that is, and the resisting force which will be acting, that is Fd, in opposite direction of flow. So when uniform flow condition is established, the driving force and the resisting force will counterbalance each other. Now, based on this pretext, let us analyze what would be the shear stress in case of an open channel flow. So in open channel flow, due to friction, it acts itself as a shear stress between the flowing water and the wetted surface. So here, if we look that the friction in the the flow. So this is the wetted surface and the flowing water. So this surface uh, will have some friction, and that will be responsible for generation of shear stresses in case of open channel. So by the definition of uniform flow, we proceed ahead, that is Fg is equal to Fd. So now what are the resisting forces? So the resisting forces is Fd is equal to tau naught P into delta x, where P is your wetted perimeter and delta x is the length you have taken, the elementary strip. Similarly, the driving force, that is gamma A delta x into sine theta, where gamma is your unit weight of water, A is your cross section, area of flow, and sine theta, that will be signifying the component in the direction of gravity. So let us equate the equations 1 and 2, and on comparing, we get the simplified version, that is tau naught equal to gamma A by P into sine theta. Now, if the values of slope, the theta is very small, then your sine theta would tend to tan theta. I mean, they will be very equal, and that will be equal to your S naught, that is a longitudinal slope, because your tan theta is your distance upon length. So that will be equal to your S naught. So very small values of theta, your sine theta will be equal to S naught, and thus your equation reduces to tau naught equal to gamma r S naught, where the term r is called the hydraulic radius, that is a ratio of A by P, that is a cross section area of flow, and the wetted perimeter. So this is a very important parameter, hydraulic radius, and it depends on the geometry of the cross section. So if you have a rectangular cross section, if you have trapezoidal cross section or circular cross section, its area and wetted perimeter would change, and thus r would change. So r is a very important parameter in this equation and further in uniform flow estimation. Now coming to the resistance equation, so there are a couple of there are, I think, 4 5 equations, but we'll discuss a couple of them which are very relevant. The first is the Chezy's equation. So there was a scientist, Chezy, who derived this resistance equation. He was a French engineer, pardon, he was a French engineer who was working on this uniform flow, and in around 1769 he coined this Chezy's equation. So the average shear stress can also be expressed as tau naught is equal to k rho into v square. So tau naught is directly proportional to v square. So the proportionality constant is this k, rho is the density of water. Now we compare the equations 3 and 4. So equation 3, that is tau naught equal to gamma r S naught. So we'll just compare these two, and on comparing and simplifying, so the coefficient k, that is a function of the nature of surface and the flow parameters. So on comparing and rearranging, we get velocity is equal to c under root r S naught, where your c is the Chezy coefficient, and that is simplified as under root gamma by rho into 1 by k. So that is your Chezy coefficients. So that brings us to one more question, whether the Chezy coefficient is dimensionless or it has some dimensions. Usually such coefficients are mostly a dimensionless number. So the hint is, just do a dimension analysis of this equation, and you will get what is the dimension of Chezy's coefficient, whether it's dimensionless or it has some dimensions. Moving ahead, uh, in pipe flow, we had a lot of discussion, or you might have studied about Darcy-Weisbach friction factor. So that Darcy-Weisbach friction factor is expressed by a very well-known equation, that is for head loss, HL equal to FL V square by 2 GD. So the F is your Darcy-Weisbach friction factor. Now, since we have already discussed that in case of open channel, you have the relationship between the diameter, that is a characteristic, so r is equal to d by 4. So you get D is equal to 4R. So for the open channel flow, the same equation is modified as FLV square upon 2G into 4R. So rearranging equation number 7 and making V square as a subject, so you get V is equal to under root 8G by F into under root R into under root HL by L. Now the head loss, the head lost in unit length, that is nothing but it is the slope of energy line, and that is equal to the bed slope, because for uniform flow condition all the three slopes are equal, so this term becomes S naught. So now the equation resembles as V is equal to under root 8G by F into under root R S naught. So if you just look, this equation will be somewhat familiar to the equation derived here, that is V equal to C under root R S naught. So just comparing those two equations, that is equation number 5 and equation number 8, so you get C under root R S naught is equal to under root 8G by F into under root R S naught. This gets cancelled and the C is equal to under root 8G by F. So your Chezy coefficient is inversely proportional to the square root of the Darcy-Weisbach friction factor. So if you are given this information about Darcy-Weisbach friction factor, then you can get the Chezy's coefficient. So Darcy-Weisbach friction factor, usually we have analyzed from the Moody's chart, where you have the Reynolds number, relative roughness, and based on that you analyze the Darcy-Weisbach friction factor. Now there is another resistance equation that is a very famous than Chezy's equation. That is a Manning's equation, which was proposed by an Irish engineer called Robert Manning, and he found that the relationship, that is V is equal to K by N R raised to 2 by 3 S naught raised to half. So this is the very well known Manning's equation which he proposed. Now this value K uh, is taken as 1 if you are using the SI system, and it is taken as 1.49 if you are using the FPS system. So the units of this K, they are, a meter raised to 1 by 3 per second, and in case of FPS, it is feet raised to 1 by 3 per second. So usually in textbooks you will find that V is equal to 1 by N R raised to 2 by 3 S naught raised to half. So when you try to balance the dimensions on LHS and RHS, you will see that this equation is not dimensionally balanced. But many textbooks do not mention that this 1 is not merely a number, it carries this unit. So that is why uh, that the purpose of this unit, that is to make the equation dimensionally homogeneous. Okay, so when you now check the dimensions, the equation will be dimensionally homogeneous. So velocity is proportional to the 2/3 of the hydraulic radius and the square root of the longitudinal slope. So in case of Chezy's equation, velocity was proportional to the square root of r. So here it is proportional to 2/3 power of r, and the discharge is given by Q is equal to 1 by N A R raised to 2 by 3, where N is your Manning's roughness, or it is sometimes also called rugosity coefficient. A is the water flow area, R is the hydraulic radius, and S naught is the longitudinal slope. So this is a very famous equation and very widely used for computing the discharge in case of open channel flows. Now, comparing equation 5 and 11, that is the Chezy's and Manning's equation for velocities. So what you get, that is from Chezy's equation you got C under R under root R S naught, and Manning's equation 1 by N R raised to 2 by 3 S naught raised to half. So when you compare, you get the relationship that C is equal to 1 by N R raised to 1 by 6. That is, the Chezy's coefficient is inversely proportional to the Manning's coefficient. So this is the relation. So if you have either one, you can compute the other one. So that brings us to one more question, that how the Darcy-Weisbach friction factor is related to Manning's roughness coefficient. Now you have already established the relationship between C and F. So how that will be related to the Manning's roughness coefficient? Again, it brings to another point. Is Manning's roughness coefficient dimensionless? Okay, so these two are the discussion questions which you need to attempt. Moving ahead, now what factors does this Manning's n depends upon? So usually it is called Manning's n. In usual discussion, will not avoid. I mean, will avoid discussing Manning's roughness coefficient every time. Manning's n usually defines that. So first and foremost factor is the roughness of channel surface. So as it is a roughness coefficient, obviously if for smooth channels it will be a low value because that will signifying less resistance, and for rough channels will be high value. So as you have noticed, Q is inversely proportional to Manning's coefficient. So higher the value of n, low will be the discharge because there will be more resistance. So lower the value of n, higher will be the discharge. So in the first case where there is alluvial channels, that is consisting of fine bed material which could be sand, silt or clay, the value of n is low because there is less roughness involved and it is unaffected by stage. That is, stage here refers to the depth of water in the channel. Now opposite to that, the gravel bed rivers, which are usually coarse bed material of gravels and boulders, they have a very high n value, especially at low and high stages. So at low stages there will be too much resistance offered by the bed material, and in case of high stages the banks will also offer more resistance. So that is why the n value will be very high in that case. Next factor is the vegetation on beds and sides of the channel. So in case of alluvial or natural channels, there is a propagation of vegetation, so that induces some surface roughness, and it tends to reduce the channel capacity and retards the flow. So more vegetation, that means it will try to offer more resistance and thus retard the flow. So next parameter is irregularities in the channel section. So sometimes in non-prismatic channels, that is a natural rivers and all, we observe that there are variations in the cross section, the size, the shape, the wetted perimeter, etc. So if these variations are gradual or rather uniform, then there is not much effect on n. But if there is some abrupt change, like sudden shift in the width, sudden change in the depth, then the values of n will be very large in that case. Next is the channel alignment. So there are two cases in that. First is a smooth curvature having a large radius. So here you can see there is a very smooth curvature and the radius is very large. So there the resistance offered is less and the Manning's n value is a lower one. While in case where there is a sharp curvature and severe meandering is there, so this is in plan what we are viewing here. So you can see that there is lot of resistance to flow due to this secondary currents being generated, and that is why the Manning's n value is very high. Next factor, that is silting and scarring. So the as a result of silting, it changes the irregularity of a channel to some sort of uniformity, and that could lead to decrease in the n value. But scouring, it will do the reverse, and that will project an increase in the n value. Again, if there are some obstructions in the river, like there are some trees which have fallen, construction of bridge, so bridge piers will also obstruct the flow, there are some debris due to landslides, then that will offer more resistance and it will increase the n value. Now again, the Manning's n is a factor of stage and discharge in a channel. So let us understand what is stage. So you are very well aware with the depth. So let us say this is your depth y. So to that y, if I add a datum, so that becomes your stage. So stage is with reference to the mean sea level. So that is stage. So that is why you are aware, in surveying we used to discuss the cross section area computation, volume computation. So at different water levels or water depths, the stages are, let us say here the stage is 150 RL, 162.8, 166.4, 170.5. This is the highest water level which has been observed in the river. So these are the different stages. So with the increase in stage, your Manning's N would increase. Now, uh, this particular curve, that is called the stage discharge curve. So while we were discussing the measurement of velocity using current meter, we discussed this. So when the velocities are measured and the cross section area is already surveyed, so for different depths of flow, what would be the discharge? That is a volume. What is the volume here? That is being analyzed, and the discharge is arrived at. So the state discharge curve, so if you have the information on stage, you can easily quantify what is the discharge at that given stage. Now, when the stage is very low, what happens, that the channel bottom, the whatever irregularities are there in the channel bottom, they are very pronounced, and their effects would be very significant in offering resistance to flow. So at low stages, if your channel bottom has so many irregularities in terms of vegetation, gravels, boulders, then it will offer more resistance. Now, let us say when it is in mid stage, the resistance will be little bit lesser as compared to that was due to a low stage. Now, opposed to that, when the discharge is too high, so when there is a high discharge, your water may spill over the banks and enter the floodplains. So when they enter the floodplains usually are very rough. The surface is very rough due to vegetation, some obstructions like building and structures, and that is why the N value will be very high when the discharge is higher. Okay, so this is how the discharge and the stage affect the Manning's N. So that brings us to another set of questions, that let us say due to construction of bridge in a river, would that increase or decrease the values of Manning N as compared to the earlier condition? So that is one more question. And the next one is, would the Manning's N vary with stage and discharge in case of a smooth lined irrigation canal? So there is a natural channel and there is a smooth lined canal, that is a prismatic canal. So in that case, whether the stage and discharge would affect the Manning's N, that is another question which you have to resolve. So last part of today's lecture, that is Manning's roughness coefficient. How would we estimate that? Now, the understanding of the factors which affect the Manning's N would all always provide us a guesswork that okay, this could be the Manning's N, because if there is a straight alignment or a meander alignment, you can guess that okay, for meander the value will be particularly high. So if you know the value for the straight alignment, let us say it is 0.018, then you can say that it will be little bit higher. You can guess it to be around 0.03 or nearby that, all of course considering into mind other factors as well. Now in Manning's formula, except the term n, all other parameters are directly measurable. You take it the longitudinal slope or the cross section area or wetted perimeter, they are measurable. Only n is not measurable. Velocity also you can measure. So if you have all these parameters, you can calibrate the value of n. So in the laboratory experiment, we perform such an exercise where we find out the Manning's N coefficient. So laboratory channel is usually a glass channel. So for that, we'll find the value of n. So the roughness coefficient would represent the integrated effects of the channel cross section, resistance, and which will be estimated. So usually the estimation of n is somewhat subjective based on one's experience or engineering judgment based on the site conditions and all. So here uh, there are some readily available tables which gives the Manning's N value. So if we don't have any values, based on this table we can judge. So if there is an open channel with concrete lining, the value will range between 0.013 to 0.022. If there is a channel which has some earthwork and all, then it will be ranging between this 0.018 and 0.020. So in this figure, you can see this is a smooth concrete line channel carrying water. So in this case, since the surface is very smooth, the Mannington is 0.013. Second, here you can see that this is a gravelly river where you have cobbles and pebbles and all. So due to that, the bed is bit rough and the value of N is higher, that is 0.024. Next is, you can see there is a vegetated river stretch where the bed and banks are composed of clay, and there are some grasses. You can see here that there are some grasses, and that will yield a relatively higher value of Mannington, that is 0.026. The third one, that the bed consists of gravels and some deposits of small fragments of rock, and there are grass also present on either side, and thus more roughness compared to the previous case. So it has a 0.027 value. Again here more roughness due to trees and boulders and gravels. And lastly, if you can see, the bed is of sand, gravel and boulder, so it is a combined distribution, that is a grain size. And there is here you can see vegetation growth and all, trees and all, so that yields a particularly higher value of Mannington. So usually for natural rivers, your Mannington may vary from 0.025 to 0.040 depending upon the condition of the river. For canals, it will be 0.030 for very new canal, because it is more smooth, and with respect to time it will get some deterioration, and it may increase to 0.015 or 0.016. Now, here I am illustrating one exercise how to estimate the roughness coefficient. So here you can see that in a river reach, these are different cross sections, and this scale bar would give you the roughness coefficient. So based on that, you can see here it is ranging in the range. This is a river, so the roughness coefficient is around 0.032 and 0.042, somewhere here. So this is the source from the Heckrest software, where we input different cross section, can model the flows. So these is the Mannington value. Distribution is given. So from analyzing the satellite images also, we can derive the Mannington value. Now, usually the natural channels, there are different factors which will affect the Mannington. So Cowan has proposed a procedure that, considering all these factors, how you can estimate the roughness coefficient. So he basically gave weightage to different factors. So the roughness coefficient, that is a combination of all these factors. So one NB is for the basic values of Mannington for a straight and uniform channel. So if your channel is straight and uniform, you give NB. Now if there are some surface irregularities, you add N1. If that is absent, you neglect that term. If there is variation in cross section, you add N2. If there is any obstruction like bridge, you add N3, otherwise there is that can be neglected. If there is too much vegetation, then this term will be added, and if there is a meandering, then this term is a multiplicative term. Thus you get the corrected roughness coefficient for your channel. Okay. And in another case, that is a last case, if the channel consists of multi roughness parameter, then what to do? So sometimes what happen, the channels are very wide, so this part will have lot of vegetation, this will be a gravelly part, this will have some sands and all, and this will have trees. So you have multi roughness criteria. So in that case, uh, what to do? So there is a Horton's formula. So it suggests that n is equal to sigma, then product of ni raised to 3 by 2 into pi the whole raised to 2 by 3, and that divided by p raised to 2 by 3. So your n is the equivalent roughness you will get for this entire cross section. So at each point like p1, p2, p3 and so on, you have the roughness and the wetted perimeter as well. So based on that, you can compute the equivalent roughness or the composite roughness. Okay, so that is all for today. In the next lecture, we will discuss the conveyance of a channel, then the section factor, how to compute the normal depth, and so on. Thank you very much.